Um, Here you see some Scala code. We have numbers, map, square, reverse. And that's the same thing as if you had said numbers dot map of square dot reverse. And every real Scala program will, of course, write this, because otherwise you contribute to the global pixel shortage. So as Scala programmers know, seriously, sometimes we do this, sometimes we don't, depending on what makes an expression more clear. But people who design DSLs love this feature because it lets them do what's called fluent APIs. So here I've taken this from a DSL for testing, and here you can see it says it should, and then there is a string in, and then there's a block of code. And so this is, of course, it dot should of the string dot in of that block. But it reads very nicely, and so one can write these tests that supposedly your manager can understand, as if there was a value in that, but whatever. Another thing that you can do in Scala that's quite nice is you can define your own symbols. So if you wanted to have an operator that looks like a long arrow, then you can make a method that's called greater, equals greater, and you just define it like any other method. You could also use any old Unicode character. So there is actually a Unicode character for this. And if you can figure out some way that your users can type it, then you can use that as an operator. And so some languages, particularly mathematically influenced languages, really like to do this. So if you wanted to build a DSL for matrix multiplication, then you can imagine that you put a bunch of math symbols in there, and your users might be able to deal with the way and how to do inputs by having some special keyboard driver for this. Or you can just define operators that are composed out of the normal ASCII set and that look reasonably like what a mathematical user would use. It's a lot better than using alphabetical method names, depending on your domain. So another thing that is nice for building your own DSL is if you can deal with code blocks in some way. So here is a code block. This was again taken from this testing language that maps X to some assertion, and it's enclosed in braces. And so it's nice that you can directly specify that in Scala. In this case here, X is a parameter to the block. What if we wanted to access X from outside? Blocks are closures, so if I just use the X in here, then it would work from the outside. Now in Scala, of course, we have these closures automatically, and they work the way that you intend to. Again, this is something that people who design their own programming language fight with. It took Ruby, I believe, 4 versions before Maths discovered that closures exist. And so it's again the idea that you're better off starting where someone laid the groundwork for you. So there's another nifty feature in Scala that one can make use of, and that is that if you want to avoid this unsightly thing here with the parentheses and the arrow for a method without parameters, then you can do that, but in the parameter of the receiver, you have to say that you want a by name parameter. Did you guys cover that? Okay, good. And then then one can consume something that really looks like a block of code. So, for example, here I'm designing a mini DSL for making HTML. I'm just pretending this is not something that actually exists. So in this case, UL would be a function that consumes a function. This function here would yield a sequence. So I'm going through some links, so this must be a map or a list of pairs. And then I would consume, I would produce out of each of them an li element. And so this thing is in a collection, this thing yields a collection, the UL executes this thing, harvests the collection, and builds out of that some piece of HTML. So you could write something like this very quickly. You would have to write functions for UL, functions for LI, and so on, and for each of the 30 or 40 elements in HTML. And you would then be able to make yourself a custom DSL that does, if you think about it, everything that PHP does, but better. Right? So, there's a couple of small things that can be useful, accidental things. Oftentimes you need to specify strings, and you can't just specify a raw string like src or href, because that would then be a variable unless you define them all as variables. But you can of course quote them, and that way you get any strings. But that's tedious, at least on the American keyboard, because the quote is reached by a shift key. Whereas if you use a symbol, when you use quote href, that's easier because the single quote is unshifted. So that's a very minor thing. But you'll see that in some DSLs, and it's just a minor trick. It's useful to have named and default parameters, just the same as in a Ruby DSL. So here I have an image, and I say source equals, and I send some file. But the other ones, the alt and the width, those would be taken from the defaults in the definition of the img function. So if you look at img, it has a default parameter here, it has a default parameter here. The named parameter means that you can say the name of the parameter and the equal of the value, and that just makes it easier to read. That way the user can, it looks exactly like HTML. You can do new avoidance. So instead of having to write new point of 3, 4, you can just write point of 3, 4 in one of two ways, either by having an apply in the companion object, or by just making a case class where you get that feature for free. And so new avoidance is generally nice because having a whole bunch of news floating around just ruins the look of your things. You can do local imports, which is kind of nice because one of the things that happens when you deal with the DSL is that you will have tricks, you will have shortcuts, and if they're universally available everywhere, then they could interfere with other stuff that you wanted. So for example, in the DSL for HTML, I might have a function A for an anchor tag, or B for bold, and what if I have variables that are also called A and B, and that's a mess. But you can limit the impact of your DSL by having a local import that's now only in this case in the block. So, so that's nice. Now, then we come to the other big thing that Scala has to offer. Everything that you can do with implicit. So Scala really has like two levels of how you can approach this. There's the easy Scala. That is where you get to all the functional features. Functions, higher order functions, collections, and all of that kind of stuff. And with that, you get kind of where you were with Scheme. And that's nice. That's a very good a subset of Scala. And then you get to the incomprehensible part of Scala, where you do things with type classes and implicits and all of that, and where you get, of course, a lot more power, where the idea is that you should be able to use the type system in some way to get stuff for you. And some of those features are useful for building DSLs as well. So let's start with the easiest part of implicit conversions. Did you talk about any of these things? Mm-hmm. Okay, good. Whether it arrived on the other end, we don't know. But, all right. So, so the easy part is if you wanted to convert, say, an integer into a fraction. Let's say we have a fraction class in a typical exercise. Then you make a function called int to fraction that consumes an integer, returns the fraction by dividing by 1, and you tag that thing as implicit, and then it is used as an implicit conversion. So when you say here 3 times fraction of 4, 5, then this kicks in. 3 is not a fraction. This thing is not an integer, so the star but naturally is not defined. And so now Scala will try to either turn this into a fraction or the fraction into an integer, and it'll succeed by doing the former with this implicit conversion. That's very useful for enriching existing classes. So let's say that I wanted to have a function where I'm having a path. So this is a Java 7 path object that references a path in the file system, and I want to read the file. Well, if Oracle had done the homework, they would have given me a method read that just reads the file. I mean, this happens so often, right? Unfortunately, that's not what they did. If I wanted to read the file for it, they do give me a function called read all bytes that gives me an array of bytes. Well, thank you very much. So if I wanted to actually read it as a string, then I have to construct a string and pass that thing to it. I don't know when's the last time that you wanted to read a file and then have it as a byte array. For me, the answer is exactly never. I always want it as a string. And so what can I do? I can petition Oracle. Back on planet Earth, I can use Scala, and I can make an implicit function that takes a path and converts it to what? Well, now I do have to define a little class that has this read method, and then I get this automatic conversion. So this is something, of course, that when you build a DSL, that you're going to find yourself doing regularly, that you have some object that's in the host language, like integers, strings, path objects, whatever, and you then lift them up into something that is a little bit more powerful so that you can put some extra syntax on that. So that's these implicit conversions, and that's pretty easy. The harder part is these implicit parameters. And so I'll briefly explain the strategy, and then I'll show you an example in the lab that'll make it much clearer. So a functional method can have one or more parameters that are tagged with the word implicit. So I'll give you an example. Here I have a function read, and it takes a path, and it's supposed to produce a string. And when you read a string from a file, there's actually a rational reason why the Java library doesn't automatically turn a byte array into a string. Namely, that byte array could have come in any character encoding. I mean, how would they know? So the file that you're reading could have been encoded in UTF-8 or in UTF-16 or whatever, the Windows code page 1252 on an unhappy day. So so one needs to specify that. And normally, the way to do that would, of course, be to have an explicit parameter that says, also specify the character set. But that's boring because in 99% of the case, the character set is hopefully UTF-8, and why have to specify it all the time? Of course, you could use a default argument for that, but another way that you can do it is you can use an implicit parameter. That's what we're doing here. So it's an implicit parameter. And now when you call this method, you don't have to specify the implicit parameter. You can, but you don't have to. And then there's a complex set of places where Scala looks for a value of this type. It'll look for a value of type, and what's this, java.nio.charset, that has to be in scope. And the set of rules for that, I don't know, did you guys do this? Okay. Yeah, and so the set of rules is complex, and I can't ever quite remember what it is either. And neither can Martin or Dursky. But it's tuned to kind of give you the results that you expect. So you can define somewhere in scope a thing of this type. Now here, what I've done is a little bit fast and loose. One would normally not do this with a standard type like java.nio.charset because, what if there happened to be one in scope like that? You normally have some custom type that you make so that, to make it more likely that they're unique. So there has to be a unique object of this class, and that's then used as the implicit parameter. So what you can do with that is you can take a value that gives you, say, some kind of configuration or some general defaults, and you can carry it through from one call to the next, to the next, to the next, to the point where it's actually needed. That's done, for example, in OR mappers. So if you've ever gone through some of the Play tutorials, the Play tutorial uses ANORM as a very simple way of writing SQL statements in a type-safe way. So at some point, when a SQL statement gets translated, the thing that does the translation needs to have access to the JDBC connection. But of course, in a DSL, it would look really ugly if you, the programmer, had to worry about feeding that connection object every time that you wanted to make a SQL call. And so what they then do is they set it up that those calls take a connection, or rather a thing that yields a connection, as an implicit object. So anytime that you want to relieve your users of the obligation of having to specify these kind of boring defaults, this implicit parameters tricks works quite nicely. So these are the things that we're going to be practicing in the lab because they're relatively simple to do and within reach of an afternoon. There are more things one can do. It is in fact not possible in Scala to redefine what x.foo is. So in a dynamic language such as Ruby, this happens all the time. Even in JavaScript, you can redefine what x.foo is by just putting foo into the map of the thing that x represents. But in Scala, traditionally, this was statically typed. And so Scala now has a feature that's called dynamics, where x.foo can be resolved in a reasonably type-safe way at compile time, so that you could use that for building your own Aura mapper, for example. And it's a bit complex, so I'm not going to talk about that today. I'll give you a link to a blog that you can check out. Whenever you design a DSL, an internal DSL, you're going to run into this point where the host language can only do so much for you, and you want to do a little bit more than that. And there's one nifty escape hatch that you have in Scala, I believe since 2.10, with string interpolation. So the string interpolation feature is the one that you love to do things like formatting. So when you say f followed by a string, then inside the string you can embed stuff. You can say $p.name, for example, %s, which means the stuff is now formatted as a string. And $height, %2.2f, which means it's formatted as a floating point number, just like it has been for ages in C, right? Except with one very nice difference. It's typeset. So if this thing was a string, it would fail at compile time. Whereas in C, as you know, when you pass things to printf that aren't right, then a hacker can take over your program. So, so you can hijack this mechanism to come up with your own strings. So say you wanted to do something with HTML, you could do an HTML double quote, and inside there have some way of mixing HTML and code. And the code you would just put into $signs. That mechanism for interpreting and splicing the $signs, that's for free. It's a general mechanism that you can use. So that's something that's nice to know. Now there are many DSLs where instead of directly executing what the user writes, they actually build up like mini parse trees. So for example, when you would imagine that you would do a DSL for matrix multiplication, and so you'd write A star B plus C. Now your first idea would be you would directly execute that. When you see A star B, you would just multiply the two matrices. When you see plus C, then you would then compute the sum of that. But what if you wanted to vectorize the operations? In that case, you would first have to know what all the operations are, and then you would, give them to your GPU to work on it or something. So in this case, there's no direct execution, but instead you first build a parse tree that gathers all of the data together, and then you run some kind of optimizations, reshuffling, whatever, scheduling on the data that you gather. You can do that by hand, simply by making classes for product and sum, and doing whatever mechanism you want to do. But because it's so common, a bunch of people at EPFL have written this nifty framework called the Lightweight Modular Staging Framework that gives you useful plumbing whenever you need to do that. So if you find yourself in a situation where you say out of SQL expressions you want to build a parse tree to deal with it later, or out of mathematical expressions or whatever. Check that thing out. It's very powerful, and it just gives you the kinds of things that you would have to do. There is a relatively new feature in Scala that's still evolving called macros, where you can define new language constructs and how they should be compiled. So you could define an assert that works like a C assertion, for example, as a very simple example. But you can put in a new statement. So if you thought that while wasn't good enough for you, you could put in an unless statement, and you could tell the compiler whenever it sees that token to call your code, and your code would then generate would then translate that code. It's a bit of a controversial feature because you can change the behavior of the language so much, and it's also really complicated. There are several rounds of efforts to try to make it simpler, but it's still a bit of a work in progress. But it's interesting to look at it. The only DSL that I know that actually is taking advantage of macros is SBT. And I'm not sure that's a testament to it, because SBT as it is impossible to understand. And I don't know that adding macros to it has been helpful. So SBT is, of course, a real life DSL that we all know and love, or at least know. And so it's a good example of that. Here's a few others that you can have a look at if you're interested. So Squirrel is another OR mapper that you can think of it as a internal type-safe DSL for SQL. Now these testing frameworks, I've shown you one. There's a whole bunch of them. Here's just if you wanted to see what people do with DSLs. Check out this link here to this guy who made a regex DSL, and you see what level of obsessive detail he went into. So obviously this fellow doesn't have a life. There is, and unfortunately my network is not on, but click on this. There is a way of doing a basic interpreter, a 1980s style basic interpreter entirely in Scala. So it has things where it says 10, where the lines are numbered 10, 20, 30, and where the actual basic instructions is very weird. So it's just for fun. I gave you something where I found this library for image processing, and it's a great Scala library. And boy, this would really benefit from turning it into a DSL by adding some features that would make it easier for users to do that processing. And of course, your very own. So you will sooner rather than later arrive at the stage where you want to do something with Scala that you want other people to use, and you want to abstract away all of the complexity of Scala and make it really easy and nifty. And so that's when you want to build your own internal DSL. So you're going to be practicing building an internal DSL with this lab. So start firing up your Scala IDE. And I'll briefly tell you what happens, and then I'll just let you go and I'll walk around and see where you get in trouble. And then afterwards we'll talk all about what we've learned. So what this DSL is going to be about is to combine effects. So you're going to be seeing some effect where a circle moves from one point to another, or where a circle grows or shrinks in shape, or becomes opaque and transparent, or where text floats around the screen. And so when you do that, and so I have to do this actually. So this comes from a personal project. When I teach like a data structures course, I want to be able to draw a linked list where the first box appears, the second box appears, and then an arrow magically joins the first to the second, and when an element then gets removed, it becomes transparent, and then one reroutes the arrows, that kind of stuff. So, and if you want to write these effects, of course you can use it as a library, and as you'll see, that's really painful. Because that's not how you want to think about it. You want to think about, oh, I want to first do this, then do that, and then together I want to do C and D. And so what you will learn to do is how to implement first this, then that, and then together in a simple DSL. All right, so get going with it, and we'll see how that goes.
You sure you don't want something to drink?
Yes, talking about how to write an external language and still use Scala for the purpose. And interestingly enough, in the context of doing so, you will see another really nifty internal DSL. So if you've ever taken a course about programming languages that involves writing your own language, you might have seen how to write a parser that reads in a program in your language, turns it into a tree structure, and then you take that tree structure to generate code. But even if you've never done that, I mean, the basic principle I think is pretty straightforward. So just imagine what the Scala compiler does is it reads a Scala program, it knows the grammar of the Scala language, builds up an intermediate representation that's a tree structure, and then it uses that to generate Java virtual machine code. And so you would do the same thing if you build your own language. And you would then either build an interpreter, something that executes the code that the user of your language supplied right away, or you would build a code generator and generate code for a virtual machine or for an actual processor. And in Scala, we have a very easy way of making the parsers and attaching behavior to them. So before I've seen this library, I used to teach students how to use a parser generator. There are these things called Yak or Java CC or Antler. And so they are systems that enable one to write a parser reasonably quickly. But it's much easier in Scala. So I'll just show you how to do it in Scala, and I'll just give you the minimal background you need to get going. So I think I've seen some slide where you had in your course where you had context-free grammars, right? So I don't have to say what a context-free grammar is. You've probably seen an example grammar. Here we have a grammar that does simple arithmetic. So where an expression is a term plus minus an expression, a term is a factor times slash a term, and a factor could be a number or a parenthesized expression. And then this grammar will produce expressions that contain plus, minus, multiplication, and division, and parentheses. And it does it in a way that the parsing recognizes that multiplication binds stronger than addition, but that the parentheses can be used to override that. So the resulting parse trees reflect the structure of the input. And so if you have such a grammar, then it turns out to be super easy to translate it into a Scala parser. What you do is you extend some superclass that does the plumbing for you, and for each grammar rule, you define a function. So expression is a function that is defined to return the funky looking thing on the right. That I'll explain in a minute. Term and factor similarly are functions. Those functions will later be launched on something that has an input text, and they will give you some kind of a result. In this case, the result is any, and you will know in a minute why it's any and not something more intelligent than that. And soon it will become something better. Now look at what you have on the right-hand side of the equal. You have this squiggle operator, and you have operators opt and a vertical bar. So these are, of course, Scala operators that combine certain things. What do they combine? Let's look at this one here. So a factor, we say, is whole number. Whole number is a function that's defined in Java token parsers that will consume the string that represents a number and return that string. Let's look at the thing here. This here is going to be converted by an implicit conversion to a parser that can only eat left parentheses. This one can only eat a right parenthesis, and it'll just fail if it doesn't find it. The thing here is a parser that's defined up here. This is a function. So the squiggle can combine a parser function and another parser function. And it's the same thing as first do this, then do that you've seen with the effects. So this is a little internal DSL for parsers that says, try to use this parser for parsing it, or if that doesn't succeed, try the parser here, which is a first try this, then try that, then try that. So the primitives that one needs is, the string returns, I say it returns itself, that's not quite true. It returns a parser that can only consume that string. Opt means optional, that's the thing that you would do with a question mark in a grammar. Rep is a repetition. This squiggle thing here returns an instance of the class squiggle, which is essentially the same thing as a pair. And I can't remember, there's some reason why they didn't just use a pair, and I can never remember. It's some trivial reason. But you should think of the squiggle as basically being a pair of the first and then the next. So if you make a new expression parser, and now you tell it to parse the string 3 plus 4 times 5, then you get back this, which is admittedly not very attractive, right? This is a pair of another pair of a object of the sum case class with some other junk in there. And that's because we right now we haven't yet told the parser functions on how to do anything intelligent with their results. They just return the result. That's also why the return type is any, because there's nothing in common between a string and a pair and a sum. So we'll fix that in just a minute. Notice, however, that when you look at this really hard, that the structure of the expression has been preserved, the 4 times 5. So it doesn't simply blindly go left to right, but it realizes that the 4 and 5 belong together more closely than the 3. So one has hope if one does the transformation more intelligent to derive some actual value for it. So that's the other thing that we use in our DSL, the operator called hat. That's used to transform the result. So when you say hat followed by some function, then that function is launched on the return value. So this is kind of like where we left off in the lab just before the break. So they're giving, just like at the time I said, we want to give the animation user a way of running an arbitrary function in the animation. Here, the parser user gets the chance to run arbitrary functionality as the parsing happens and to transform what was being read into the result that we want. So here, when a whole number, it comes back as a string by default. Well, I don't want to, what am I going to do with the string? So I'm going to run this function here that converts it to an int. And now I have the value as an int. I'm actually going to do that with all the others as well. I'm going to make it so that they all return an int. And you can see that now the any is going to be changed to int. I'm going to simply evaluate what the expression is in this particular example of the parser. So let's see what xper was. On the previous slide, xper said it's a term followed by, optionally, either plus or minus, and another expression. Now I'm going to evaluate it. So here's my evaluation function. Oh, by the way, why is it hat? Does anyone have an idea why they use this? As opposed to, say, arrow or some such thing. So trivia fact is that the precedence of one of these Scala operators, you can define any operators that you want in Scala, and there has to be some precedence rule. It goes by the first character, and then it says it's the same precedence as in C and Java. And so the hat has a very low precedence, and so it means that you can first do all these other operators here, and they're not going to be affected by the hat. You don't have to use an extra set of parentheses. That was the only reason. Why they use 2 hats instead of 1, don't really know. So the function here uses a partial function syntax with a match here, like a match expression. So it says, if this thing has the form something squiggle none, because the opt returns a Scala option, then the value should just be whatever the left hand side. If it was a something squiggle sum of a plus and a b, then compute a plus b, and otherwise compute a minus b. So this thing takes advantage of pattern matching in Scala. You've seen this, right? Mm-hmm. So these are just expressions with case classes, and so Scala knows how to destructure case class expressions. And so there's nothing new here. This is just plain old Scala that can, in the normal destructure. This expression function now returns an integer, and it computes whatever the first one computed plus or minus whatever the second one computed. Notice that here I have to say x per, and I had to give a return type for this function. Whereas over here with the factor, I didn't have to give a return type, or I didn't anyway. And the reason is that this is a recursive function. Scala can do type inference for any function except for recursive functions, so I'm forced to put in the return type. You'll notice that in the lab there'll be one spot where it's easy to forget. So now I've transformed everything to ints, and that's it. There's one final thing that's kind of nifty when you write these parsers, and that is when you look at the rule for expression. So, sorry, for factor. Factor had two parts, the whole number that we already know how to do. And then there's the expression part. The expression had a left paren and the expression and the right paren. So sure, I could now write a function. That function would now consume a something squiggle, the thing that I actually want squiggle, the right parentheses, and then I could discard those by just fishing out the middle thing. But there's this squiggle arrow operator, or a nifty shortcut that say, when you parse this thing, this part has to succeed, but then you can throw it away. And so this thing here then returns, it throws away the left and the right, and the remaining thing is the expression, which through the miracle of recursion gives me some parse value. And that's how you would write a parser that can transform these expressions. But that's not what I want to do. Come on. What I want to do is, of course, parse animations. So we want to have a library for we want to have a grammar for these animations so that I can say, that my user can say, I want a circle that is bounded by, like I said, I don't even know, this must be typo. So forget the 40. I want a rectangle like this. And then I want to move this rectangle to this point in this direction, and afterward I want to move it to some other place, and I also want to hide it in 1500 milliseconds. As you can see, this is not the world's greatest language.Maybe I should put in like some seconds in here or some x's and y's to make this easier to read, but I'll leave that as an exercise to the ambition. So I've come up with the simplest language possible here so that one can easily parse it. I'm giving, oops, come on.
Maybe something they add?
Yeah?
The external DSL here means that what we write, what the user writes, is not written in Scala itself. It is in a different file. It can be defined in a different file. So the user is able then to write something like, it is written in C, here, circle, blah, 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 and then it will be parsed and it will write Scala with the objective.
And actually, how can you tell that this can't possibly be Scala? So I could not make this with an internal Scala DSL. Why not? Excellent. The comma, right? So this would not, there's no way that I can put the comma like that into Scala, which is of course why I used the comma. So if you wanted to do something, or if you wanted to use the keyword with, for example, without the backticks, right? I mean, normally the reason people write these external DSLs is because there's been some history that they've done it before like that. So right now, I happen to be doing some consulting for some company. They do differential equations of how car parts get deformed, and they have a DSL to define, what a spring looks like, or what a bumper looks like, or something like that. And so they would be keenly interested in parsing what the customers have been using for some number of years in this way. So here we have our grammar, and where the drawing is. Oh, I need to explain just a little bit. One feature of this DSL. I need to have the ability to reference objects. So if you look at the circle up here, that means it should just draw that circle. When I have a rectangle, I need to be able to reference over here. So I need to be able to say, I want to move this particular rectangle. I have to give names to variables. Now in an internal DSL, you never worry about the stuff because there's already a notion of variables in your host language. But in an external DSL, you have to do variables by hand. And you'll see later how that's done. So we'll actually make ourselves a little hash table that maps strings to objects. So a drawing contains a sequence of things that are drawables, which may be named by identifiers. And right now I'm just supporting rectangles and circles. I'll leave it as an exercise later to add arrows and stuff like that. So the rectangle is parsed like this, the circle is parsed like this, and you'll see that I had one number too many. And now I have a way of making effects. I say an effect is either a term followed by maybe another effect. The term is a summand with maybe another term. The summand is either a simple effect, which is move or hide, but the other effects I'm going to put in later. Or again, the thing with the parentheses, where it goes back here, exactly like I did for the grammar that you just saw. And move and hide, you have this particular format where you have to identify off the thing that's being moved or hidden, the duration, I don't even remember which one is the duration, and for the move, the coordinate, for the hide, just the duration. So, then I'm giving you the outline of the parser. And I'm doing exactly here what's been done for the expression parser. So I've translated everything to a def, and I've left a few blank spots, so that's something for you to do. And so go ahead and do that and write this parser. That's not a hard thing to do. The next step is a little bit harder. Namely, you want to be able to parse results. So what one wants to be able to do is that in the case for rectangle, for example, we want to actually produce a rectangle. And you can see that in the sample code that I'm providing. There's the cat, and inside here there's the code to produce the rectangle. Notice again I'm using this nifty case statement so that it destructures this expression into the parts. And I can just do so. So go ahead and start coding away. And there's a fighting chance you get it done in 15 minutes. And if not, you'll get enough done that you get a feel for how this parser combinator library works.